Hello, everyone. So this video I'm making to go over some of the examples we didn't have time for in class on Newton's laws of motion. So this is the first problem we skipped. A box of mass m. So one thing your graders have been complaining about during in grading your exams is that you are solving all problems just plugging in numbers right away. So we're gonna try and just we're going to remain using the variables only, and then only at the very end plug in the numbers. Right? So a box of mass m is being pulled by the applied force Fp at angle theta above the horizontal frictionless ground. Find the acceleration of the box and the normal force exerted by the ground on the box. So um, remember the steps that we want to use to solve any uh, Newton's laws problem, and that is to draw a free body diagram. So we choose our object is the box. We're focusing on the box. We want the acceleration of the box and the normal force on the box. So our free body diagram, the object is the box, and we want to draw the distinct forces acting on the box. So there's this applied force that is at some angle theta above the horizontal, and that's Fp in magnitude. And then there's always mg pointing vertically downwards. And so the box does not go into the ground as well. So there's also this normal force that's helping the applied force, most likely. So there is, if the applied force grew and it kept getting, if this force right here kept growing in magnitude, then there's a point where, so let me start over. So these two forces need to have vertical components that will balance mg. So if Fp grows in size, then n is going to decrease in size. And there's at a certain point, n is going to decrease down to 0. So there's a maximum Fp before the box starts to lift off the ground. But we're going to assume that the box is not lifting up off the ground and that there is still some normal force still there. So these three forces are the things acting on the box. And the next step is always to write down Newton's second law. So the sum of those three vectors is equal to mass of the box times the acceleration of the box. And this is a vector equation, so we need to separate this out into components in order to work with it. So let's have the sort of the standard x plus x direction to the right and plus y direction upwards. So in terms of the x direction, so sum of fx components is equal to max, and sum fy is equal to may. Now the box is not going to be flying off the ground. If it was, then we would have to be given a lot more information in the problem about the box's lift off and all of that. It's implied in the problem statement that the box is not going to lift off the ground. So the motion is going to remain horizontal here, which means that AX is possibly non-zero. We're not going to set AX to 0, and we can't, right? If we just look at the free body diagram, there's a rightward component of Fp that can't be balanced by any other force, right? There's no leftward force. So there's definitely a non-zero AX piece. But because the box doesn't lift off the ground, we do know AY is equal to 0. So for this y component equation, we can set some of the forces in the y direction, or some of the y components equal to 0. And so if we look at the left side of this equation, well, there's two forces that have a non-zero y component. There's Fp, but only part of Fp, right? It's Fp times sine theta that is pointing in the plus y direction. So for this right triangle right here, this piece right here is Fp sine theta. And that is the vertical component of Fp. We have Fp sine theta minus mg is equal to 0. That's the y equation. And from this, we can solve for we know, okay, so sometimes when you work in terms of variables, you can get confused with what exactly are your knowns and your unknowns. But we're given Fp, so we already know Fp. We're allowed to use Fp in our answer. We're allowed to use m in our answer. We're given m. And we can always use g as 9.8 meters per second squared, right? We're given theta here. right? So we actually have all these things. Um, so they actually gave us a lot of information in this problem. And actually we should, oh, there's one other force. So, okay, so this is also good to see. Like right now, this would give us an equation that something non-zero is equal to 0. Okay, so that's bad. There's one force that I'm leaving out the y component for, right? And that's the normal force. So there's still the plus n. And this is the thing that we don't know, right? This is our unknown. So this is equal to 0. And this will let us solve for the normal force. So this is good. We know all the other ones. So n is equal to mg, right? When we move the mg over to the right-hand side, it becomes plus, and then minus fp sine theta. So you can plug in numbers for that. I'll put the number when I post the lecture notes. I'll put the number, but it's more important that we actually get the symbols right, rather than actually getting the right number out. Okay, let's see what's going on in the x direction. So the x direction, it's just fp cosine theta. It's equal to max. And so we can solve for the acceleration of the system. So we know fp, we know theta, and we know m. So we would just plug in those three numbers there to solve for the acceleration. But keep in mind, we kept the x and the y equations totally separate from each other, right? Totally separate. Okay. So this is a quicker question that we skipped. You can try pausing the question and answering this on your own. A book is held up against a vertical wall with the applied force shown. What is the direction of the normal force on the book? Well, the normal force is going to be normal to the wall. Right? So there we have a wall right here. A lot of times we symbolize it like this. This is the wall. And the normal force is just away from the wall. So this is the normal force of the wall on the book. So it looks like it's directed to the left. Okay. So suppose we kept this problem going, actually, and we wanted to know how big that normal force was. Well, it looks like, so there, if we again, we drew a free body diagram of all the forces acting on the book. Looks like there's an applied force like this, call it F cap for applied. And that force is making an angle theta relative to the horizontal. Right. There's a normal force from the wall that's pointing to the left, and then there's mg. So we can start to relate these forces to each other. So again, from Newton's second law, we can get two different, so this is a vector equation. Sum of the forces is mass times acceleration. Let's say it's equal to 0. So let's keep the problem going. Let me write this in the notes. Keep the problem going. Assume no friction. There was nothing in the problem originally about friction, and we would have to make a few more assumptions. So we'll focus more on that next week. But if there's no friction and if the book is at rest, so that's part of the problem. It's held up at rest. So we can set the sum of the forces equal to 0. So in the x direction, what this is telling us is F applied cosine theta. That'll give this piece. So F applied cosine theta minus n is equal to 0. And then the y direction is telling us F applied times sine theta minus mg is equal to 0. So depending on what we're given, we can solve for some unknown quantities. So we would have to know all but two of these quantities, and we can solve for the other two using these two equations. Okay. Find the acceleration of the system. So remember this problem, we were holding the cart M2 at rest here, and we could figure out the tension in the string was M1G. And then we let the cart go and let M1 and let the system accelerate. And knowing that the acceleration of M1 was downwards, told us that M1G had to be bigger than the tension, or the tension went down relative to what it was before. So instead of the tension being equal to M1G, it's less than M1G when the system is allowed to move. So this question is saying, well, find that acceleration. Find what's the acceleration of the system. So it's going to be less than gravity, right? Because the free body diagram of M1 is there's M1G down, and then there's some tension. And the tension is not as big as M1G, but it's something. And so because it's something, it's not just gravity that's pulling it down. So the acceleration of the system, we already know our answer is going to be somewhere between 0 and G, 9.8 meters per second squared. Okay, so let's call A. So let's call the downward direction positive here. We know M1 is going to be moving downwards. So let's say that um, A is the magnitude of our answer, the magnitude of the acceleration of the system. So it's definitely acceleration of M1 is downwards and M2 is to the right, the same amount, but we're going to focus on M1. Okay, so let's see. We have M1G minus tension is equal to M1A. This is F equals ma. Sum of the forces is mass times acceleration for M1 in this one dimension. All of the forces are acting in the up or the down direction. So down is positive. That's why M1G was positive. And tension is in the negative direction here. That's why this came with a minus sign. So as long as M1G is bigger than tension, then you're going to have a positive acceleration, which makes sense. So then if we focus on M2, it's the tension. So on M2, there's really M2G in the vertical direction. There's a normal force upwards. But if we just focus on the horizontal direction for M2, we have tension is equal to M2A. So we have two equations for a couple unknowns. What are our unknowns? We don't know tension, and we don't know the acceleration, but we do know the masses of the two carts, and we know we can always use G as 9.8 meters per second squared. We don't want to plug in the number yet, but we want to treat it like it's just a number that we know. So we have two equations for two unknowns. You can solve by substitution, right? Just take this and plug it in for t. But I want you to get used to a method that we're going to use more often, and that is solving by elimination, if you remember this from a math class. So if we add the left-hand side, so you'll notice that the left-hand sides of the equations, if we added these two left sides together, this minus t is going to cancel with this plus t. We have m1g. We call this equation 1 and equation 2. This is going to be equation 1 plus equation 2. And what we mean by that is that we're going to add together the left-hand sides together and set that equal to add up the right-hand sides together. Right? Like if 1 is equal to 1 and 2 is equal to 2, then 1 plus 2 is equal to 1 plus 2, for example. So doing that, the tensions will cancel out, and which gets rid of, it eliminates one of our unknowns. And what we're left with is just our unknown A. So it looks like we get the acceleration is m1 over m1 plus m2 times g. So if m1 was equal to m2, if these two masses were equal to each other, then the acceleration would be half as big as normal, 1/2 g. So you want to think about certain limiting cases, right? You can imagine the case where m1 is much, much bigger than m2, or the case where m2 is much, much greater than m1. So if m2 is much, much greater than m1, let's look at this bottom case first, then this denominator is basically just m2. You take m2 and you add a really, really tiny thing to it, it's just m2. And m1 divided by m2 is a very, very small number. So then A is about equal to m1 over m2 times g, which is about equal to 0. Right, and this makes sense because if you have something, imagine you had like a super, super massive rock here. I mean, really, this problem doesn't have friction, so you have to imagine a rock on like ice. So it can actually move. You can move this rock, no matter how heavy it is, but it's really difficult to move it. And then you attach something relatively light to it. Like, yeah, it'll move, but just barely. Like the acceleration is going to be very, very small. Now let's look at the other limit. Let's look at the limit where the thing that's hanging, m1, is much, much more massive than the other object. So if we look at this, so again, looking at the denominator first, m2 is very, very small, and when you add that to m1, you basically just get m1. And then you have m1 divided by m1. So this is just the acceleration is about equal to g. which makes sense because if you're attaching, imagine this is an elephant and you attach a fly to it right here. The fly is not going to hold the elephant back from falling at all. So the elephant's going to fall down basically in G. Okay, so what we just did by considering these two cases is it's called checking limiting cases. And this is a good way of checking your answer, double checking your answer. Check limiting cases. Another check we can do is dimensional analysis. A mass divided by a mass is dimensionless. So we have a dimensionless number times an acceleration, which should give us an acceleration, which is good. Right? If we had like mass times g squared was equal to a, there would be something wrong with that. Acceleration squared can't equal an acceleration. Okay, let's try this one. Two total forces act on the box to the right. Only one of the two forces is shown. Okay, so this what's shown right here is not a free body diagram. Be very careful, and you definitely don't want to do this. Whoever drew this is a bad person. Okay, the author of your physics textbook is a bad person. They drew this acceleration here, but really they did this to try and confuse you. So, but we're smarter than that. We're not going to let them confuse us. This acceleration is a result of adding up two forces. So we need to find another force so that when we add it to F1, okay, so we need some other F2. We don't know where F2 is pointing. F2. And then we want F1 plus F2 to point down and left. Or in this direction, it'll be called F3. Okay, so remember the net force, when we add up F1 and F2, that is going to give a resultant force, F3, and that's going to point in the same direction as the acceleration. Okay. So we don't know what F2 is, but we know the direction of F3 and we know F1. So if we take this equation and solve for F2, we get F2 is F3 minus F1. So if we took this downward acceleration, so we want to be careful because this is, we're plotting an actual force, not an acceleration. We're plotting the net force. This is going to be F3. It's going to point in the same direction, but we don't know the magnitude of it. So F3 points that way, and then we're going to add together negative F1, right? Subtracting a vector is the same thing as adding the negative of the vector. So F1 is pointing to the right, negative F1 points to the left. F3 plus F1 is going to point in the direction of F2. So yeah, actually that picture was roughly right. F2 is going to point somewhere in this direction. But based on this idea that you have F3 is pointing down and left, and then you're moving it to the left, or then you're adding in a vector that's pointing to the left, your resultant, this F2, is going to point down and left in this third quadrant. Right? The x component is negative and the y component is also negative. Okay. So what we needed here was F3 points in the same direction as the acceleration. And we use Newton's second law for that. Okay, a ball moves along a circular track on a horizontal frictionless tabletop, as shown. We're looking at the horizontal track from above. Right, so there's no gravity here. Gravity would be like into the page. But it's not up or down or left or right on the page. Suddenly the track ends and the ball exits the track. So as soon as the ball leaves, there's nothing keeping the ball moving around in a circle. So this is actually Newton's first law. Right? If there's no forces acting on an object, then there's no change in the velocity. So the ball is not going to change its velocity. It's going to move straight. It's going to be path C. Another example. So this one we did actually go over in class. So it's kind of a surprising fact, but so if you have two masses connected on a pulley like this, it doesn't matter where they are. Like it doesn't matter that mass 2 is higher than mass 3. When we're drawing the free body diagram for mass 2 or mass 3, the actual position doesn't matter at all. Like the gravitational force on this one is just as strong as the gravitational force on this one. Right? The gravity is not getting weaker as we go higher. So remember, it's mg, no matter where we are. Mg here or it's mg here. And so, as we showed in class in some detail, this is actually in equilibrium. And we showed in class that the acceleration was 0 here. So are these blocks in equilibrium? Yes. Okay, so what if the masses were not equal and we wanted to solve for the acceleration of the system? All right, let's try this. And we're told, well, this question's kind of weird because the second part says, would it affect your answer if M1 were higher than M2? Oh, okay. So I guess they mean physically higher, like higher up, like right here. I was thinking that the value of the mass were bigger than the value of the mass. So let's just take, it doesn't really matter which we assume here. Let's assume M2 is bigger than M1. Well, we don't really need to assume this. So really what we're going to say is if M2 is bigger than M1, then the acceleration is positive. Okay, so what we're doing here is we're defining the positive direction. Positive direction is going to be down for M2 and up for M1. Okay, so if M1 goes up and M2 goes down, that's positive acceleration. So if M2 is bigger than M1, then the acceleration will be positive. We'll have an answer at the end that satisfies that. But that's a choice that we're making right now in introducing the coordinate system. Okay, so we want to draw a free body diagram for both masses. M2 has M2G and tension. And M1 has M1G and the same tension. So mass 2, so the sum of the forces on M2 is equal to M2 times A. So the equation that gives us, keeping in mind that the downward direction is positive for M2, M2G, that's positive, minus tension is M2A. And then if we do the same thing for M1, we have the tension, which is now in the positive direction. So tension minus M1G is equal to M1A. So again, we have two equations for two unknowns. We don't know the tension T, and we don't know the acceleration of the system A. But again, we're going to solve by elimination. So if we add up the top equation and the bottom equation, the minus T cancels with the T, and we get M2G minus M1G is equal to M1A plus M2A. So if we solve for A, we get M2 minus M1 over M2 plus M1 times G. And notice how this satisfies this assumption at the beginning, or this statement at the beginning, that we defined acceleration such that if M2 is bigger than M1, the acceleration is going to be positive. So if M1 is bigger than M2, our acceleration is negative. That's just the sign convention we chose. But notice how it didn't actually matter where M1 was, right? The fact that M1 was lower than M2 didn't matter. Right? M2 is still going to go down and M1 is still going to go up if M2 is bigger than M1. And that's true whether the masses were like that or if they were like this. Okay, I think there's one more Newton's second law problem, and then we have a couple Newton's third law problems to do. A chair is sitting on a horizontal floor. Try and draw this. I forgot how to draw a chair. Looks like that. Okay. You push on a chair with the force F applied that is directed at an angle theta below the horizontal. This will look something like that. F applied. And the chair slides along the floor. Okay, so notice how there's no question asked. There's just a problem set up. And this is nice because actually you should be able to write down a list of all the questions that could be asked in a situation like this. You have the chair. So one question would definitely be, can you draw the free body diagram? Um, so we have mg, we have F applied, and the chair is on the floor, and it's the floor providing a normal force that prevents the chair from crashing through the ground. We need this normal force here. Notice how there's no vertical components of either of these two forces. The normal force is definitely going to balance those two up. Okay, so Newton's laws. So in the vertical direction, we have N in the plus Y direction, and then there's the other two forces have a negative vertical component. So we have minus mg minus F applied, and try and pause the video and figure out whether it's cosine theta or sine theta right now. This is one of the harder parts of the question, right? Is that cosine theta or is that sine theta? Pause it and make a guess, or not make a guess, but make a right triangle and figure out which it is. Okay, so if you drew this right triangle, this is theta and this is F applied, then the vertical component is F applied sine theta is the magnitude there. So we have F applied sine theta in this equation is equal to 0. So this tells us the normal force is mg plus F applied sine theta. So that's one piece that we get from the y direction. We're going to call this x direction, y direction. So then in the x direction, what we get is F applied cosine theta. That's the only force that has an x component, F applied. The other two forces don't have an x component. So that's the sum of the forces in the x direction is equal to m times ax. So ax is F applied cosine theta. So those are the two pieces of information we can get out of this. The normal force and the acceleration. Okay, so then we did a bunch of Newton's third law problems. This is one that we skipped. Which person experiences the larger average force when these two run into each other? Well, when these two crash into each other, there's this small, nerdy-looking cartoon character and then the big alien-looking football player. When the two collide, what a lot of people want to say, not outside of a physics class, is that this exerts a much larger force on this guy. But from Newton's third law, we know that the two forces are equal and opposite. This person is pushing just as hard on this person as vice versa. So both experience the same force at all times, and therefore they both experience the same average force over the time of the collision. So these two people experience the same force, but that doesn't mean they experience the same acceleration, right? If this force on one is equal to the force on person two, let's call this lowercase m and this is capital M for the lower mass person and the bigger mass person. This means m times his acceleration is equal to this person's mass times their acceleration. Call it m1a1 equals m2a2. And the one with the bigger mass has the smaller acceleration. Right? So this is why this person gets hurt and this person not so much. This person is going to feel a change in direction much quicker. And their whole body is going to change direction very quickly, and that puts a lot of internal forces on their body. That's why again, grabbing someone on the street, they're going to say this person feels a much bigger force. But yeah, the internal forces are more pronounced and noticeable on this person. But the actual interaction between these two are equal and opposite. So the small guy experiences this bigger acceleration. Okay, and this is true even if this person's at rest and this person comes in and collides. There was nothing dependent on these people moving equal and opposite directions, for example. Okay, so I think there's two more problems. Okay, so there are 8 books arranged like this, and Tom is pushing on all 8 books. So Tom is pushing on book 1, but These can be considered all one object as well. So it's up to you whether you want to group all these together and just pretend they're like all glued together or something. Or if you want to consider one separate from, say, these seven, or you want to consider these seven separate from eight, you can arrange these in a whole bunch of different ways. And what we're asked about is, well, we want to compare the contact force between 1, 2 and 7, 8. Okay. Okay. So let's say that each block has mass m. Each block has mass m. So the total, m total, for all 8 is 8m. Okay. So we can draw a few different free body diagrams. So let's draw a free body diagram just for block 8 by itself. If we're looking at just block 8 by itself, there's a contact force from 7 on 8. So it's F78 is what the problem statement has called that force. Okay. And then for all these free body diagrams, there's also gravity. There's also a gravitational force and a normal force. So N8 and FG8. But those two are going to cancel out, and all the interesting stuff is happening in the horizontal direction. So we can kind of ignore those. So Newton's second law says F78 is equal to ma. And that's it. So let's pause that. So that's going to be some useful information because we're going to get F12 is going to be something else times ma, a number times ma. Maybe that number is 8, maybe that number is 1/8 or something. So we're gonna hold off on this info. This info is going to be useful, but not quite yet. Okay, so now we want to compare that force to the one that's acting between blocks 1 and 2. Right, so let's see. So if we group together blocks 2 through 8 all together, so I'm going to have 2, 3, 4, 5, 6, 7, 8. Did I count that up? 2, 3, 4, 5, 6, 7, 8. I drew one extra. Oops. Okay, so we're going to treat that as one object. There's only, if we treat 2 through 8, books 2 through 8 as one object, then F78 does not appear on this free body diagram, right? F78 is 7 pushing on 8, and 8 is pushing back on 7. That's an internal force. When you're drawing a free body diagram, you want to draw all the forces that are external to that object. This force appears on this free body diagram because it's book 7, which is outside of this free body diagram. This free body diagram is only for book 8. So if 7 is pushing on 8, then yes, you have to include that force on this free body diagram. But here, 7, 8, and 8, 7 are going to cancel each other out because they're both internal forces. So the only force on this collection of books that's moving the books is F12. F12 is the contact force between 1 and 2. 1 is pushing on 2 to the right, and 2 is pushing on 1 to the left. So treating 2 through 8 as one object, well, if 1 is pushing on 2, 1 is also pushing on the collection 2 through 8. So again, there's this there's a gravitational force for this collection of blocks and a normal force on this collection of blocks. It's not so interesting, or not so relevant here, I should say. Sum of the forces on 2 through 8 is equal to the mass of 2 through 8 times acceleration, where it's the same acceleration, right? The acceleration, this A is the same as this A, because all blocks 1 through 8 all have the same acceleration, same A. And that's what's going to be useful to compare our two results here, same A. So the mass of blocks 2 through 8 is 7m, because there's 7 blocks there. So if we compare these two expressions, this one and this one, looks like one of these is equal to ma, one of them is equal to 7ma. So if we compare these two, we can write F12 is equal to 7 F78. And in particular, the problem says, what's F12 over F78? Well, if I divide both sides by F78, I get 7 for that ratio. It looks like the answer is 7. Okay. Okay, last problem. A block of mass MT sits on top of a block of mass MB. The bottom block rests on a frictionless ice surface. So we have ice, we have a bottom block, and a top block. MT, MB, and the ground. A horizontal push is applied on the bottom block. Okay, so I'm going to draw this push here. I guess I have a tendency to have the tail of an arrow start on the object. Um, some people might draw it this way, but yeah, I'm gonna stick with this. As a result of the push and the fact that there's friction between the blocks move to the right with the same constant acceleration. Okay, part A says draw free body diagram for both blocks T and B. Okay, so the top block has MTG. There's a normal force, and the normal force is a normal force from the bottom block upwards on the top block. Okay, so we got to be a little careful here. I'm not just going to call the normal force N because there's two normal forces in this problem. There's one from the ground on MB, and there's one on MB from NT, and vice versa. So this contact force, normal force, and this contact force, normal force. So let's decide on a label for each of these two. We'll call this N from the ground. And we'll call this NB for the normal force between the two blocks. So NB, the B stands for blocks, and the G stands for ground. So the thing that's supporting MT here is the normal force between the blocks. And in particular, it's from the bottom block on the top block. And so we're pushing horizontally to the right on on the bottom block, but the top block accelerates to the right. It also has a force to the right. And the reason for that, we're told, is the frictional force between the bottom block and the top block. So there's a frictional force, F. Lowercase f is the symbol we use for friction here. Now, if we draw the bottom block, so two of the forces on the top block were from the bottom block. And that means that from Newton's third law, there has to be an equal and opposite force on MB from MT. Okay, so these two forces have their Newton's third law pair on the other object. Right? So these are Newton's third law pairs. Newton's third law pairs. There's two pairs. There's NB, the normal force, and lowercase f, the frictional force. So you're pushing on MB. MB would slide underneath. So imagine the two blocks and you're pushing underneath. If there's absolutely no friction, then the top block would just stay there and they would rub against each other. But because of this rubbing is dragging the top block to the right and it's slowing down the bottom block. The bottom block feels some resistance in going to the right from this frictional force. And these are the two forces that we're seeing right here in these frictional forces. So in addition to those two forces on MB, we have the push from before. That's the other horizontal force, and that's the whole reason MB goes to the right, even though there's a frictional force on it to the left. And there is also the gravitational force on MB. This is MBG. And there's the normal force from the ground. Okay, so that you should have 5 total forces on MB. Okay. For each force on, okay, so we're done with part A. We've done the free body diagram for both those blocks. Part B, for each force on block T, the top block, give the other force from Newton's third law. We'll give a full sentence for each. So there's an upwards normal force from B on T. The Newton's third law other force is a downwards normal force on B from T. Okay, that's the first one. There's a rightwards frictional force on T from the bottom block. And the Newton's third law pair is a leftward frictional force on MB from MT. The last one is this gravitational force. So this is a totally different force, right? This is not a contact force from the bottom block. This one's from the Earth. So this one is the Earth is pulling downwards on the MT. And the Newton's third law pair is there's an upwards gravitational force on the Earth from the top block. Now to answer part C, we want one more piece of information, and that is to relate the acceleration of the system to the push. So I'm going to draw one more free body diagram, and that is the two blocks together. Okay, so I'm going to draw this little Tetris piece right here that is the two blocks considered as one unit. So on this object, combined object, there's no frictional force. Right? The only thing external to this object is the ground, and there's no friction between the ground and the bottom block. So there's only the horizontal push. There's the total mass of the two together times g, and then the upwards force from the ground. But what this tells us, so then from Newton, looking at this free body diagram and looking at F equals ma, and really we just care about the horizontal direction. Some of the x components is max, m total ax. So what we have here is the push is equal to mt plus mb times acceleration. So the acceleration is p over mt plus mb. Okay, so that's the acceleration. But we weren't asked for the acceleration, right? We were asked for the frictional force on block B. So the frictional force on block B is equal to the frictional force on block T. Frictional force on MT. And the reason I'm going to look at MT instead of MB is that looking at these two free body diagrams, which one's easier? Which one would you rather work with? I would rather work with this one. This one, there's only one horizontal force. I can easily get the frictional force on that. This one, it's going to be some combination of P and F, lowercase f, that gives us the acceleration. So if they're equal anyway, if they're equal frictional forces anyway, I'd rather focus on this one and then set the answer equal to that. So looking at a free body diagram for MT, so we have F is equal to MT times the acceleration. Right, the acceleration of just this block is the same as the acceleration of the two blocks together because they move together. Right? We're told in the problem statement they move together with the same constant acceleration. So that frictional force is mt times a, and this a is what we're going to plug in for that acceleration. So the answer is mt over mt plus mb times the push. So remember, there's this p right here. And so from dimensional analysis, this makes sense, right? That the mass divided by mass is no dimensions, but then the P, the capital P, is a push, a force. And a frictional force is also a force. So it looks like we have a force is equal to a force, which is good. Okay, I'm done with all the problems, marathon of problems. I hope this helps in solving all these Newton's laws problems you have on the homework. Good luck.